Hello, friends, and welcome to another Fun Times with Statistics episode. Sorry, I was just adjusting my mic and my sound. There we go. So today we're going to be talking about hypothesis testing. Just as a quick little review, last week we looked at what are called confidence intervals. Confidence intervals were a tool designed to help us, estimate what a parameter is. Today we're going to be looking at a new tool for inference that takes us in a different route. We're going to be looking for, hey, if I have a population that I know something about and I have a claim about that population, can I test to see if that seems to be a reasonable claim or not? It's going to get weird. Okay, so you notice that I've crossed out a bunch of outcomes because there's a bunch of stuff in this chapter that we do not traditionally do in Stats 1. Outcome number 2 and number 6 are about types of errors, and those types of errors are stuff that we usually reserve for Stat 2. I mean, not usually, we do them in Stat 2, not in Stat 1, so you can just, skip those sections when you see them if you read the textbook. And then you'll notice in particular outcome number 5 and outcome number 1 say the same thing. Not really sure why that happened. Anyway. So what we're going to be focusing on is building hypotheses for applications for a single mean or a single proportion. We're going to be testing those using two different methods called the p-value and critical value approach, and then we're going to use those to make a decision and write a conclusion. So today is going to be focused on a very formulatic process that has 5 steps that hopefully will help you make good decisions about business. So why hypothesis testing? Well, hypothesis testing is really about making inferences. So just as a reminder, inference means taking the information I have and using it to make predictions. So we use this in business a lot to decide decisions or if things have changed over time. So for instance, if you know that typically your average sales in the Northwest region is around $4 million, but it varies from year to year with a spread of about $500,000, what's a reasonable amount for you to experience? Or if you notice your sales drop to like 3 million this year, is that an unusual value or not? Can I determine if this is a sign that my sales in that region are dropping? Are they reducing? Is it changing? And that's what hypothesis tests are good for. Can I detect a difference with the current data I have based on a new sample? Get the idea? I hope so. If not, as we start to get into them, hopefully that'll help. So we're going to be doing 2 of these. We're going to be doing the ones for means and one for proportions. I'm going to start out with just means and then move into proportions. And then as always, you'll see I have a bunch of additional example videos for you to watch. All right, formulating a hypothesis for a mean. So we're going to look at 2 different types of hypothesis. Our null hypothesis is always our starting hypothesis. So it's the one down at the bottom with the H and the 0. The little O there stands for null or starter. If you remember anything from physics, if it doesn't give you nightmares, that was always your start or initial position, or position 0. This is the one we start with. You'll notice that the null hypothesis, or the HO, is always a statement about equality or sameness, or things not changing. As I like to say, I think of the HO as the boring hypothesis, or HOs are boring. Feel free to think about that what you want, because it's always the one that says, hey, nothing new happened, nothing's going on, nothing has changed from what we've seen possibly. And then the HA, or the alternative hypothesis, HA down here at the bottom, ha ha ha, that guy. The alternative hypothesis, also known as the research hypothesis, is always the thing you're interested in finding out about. It's the one that you suspect might be happening, or the change you might be expecting, or the thing that you have a claim about that you are testing. So just to keep that in mind, the alternative is always the more interesting of the 2 in my mind. HOs are boring. Alternatives is what you're investigating. All right. I've already said this, but the HO is the status quo. Notice it's always a statement about equality. So for instance, this first example I have is the mean filling of a cereal 16 ounces? So when you look at this, the HO is, I think it is 16. The alternative, the HA, is I think it's not 16. So notice it's a not equal to if I'm trying to decide if it is that or not. So is it this or not? The not equal to is always going to be our default if we're not sure which direction something is going. Speaking of direction, let's look at the second example. We think that Goodyear's tires will last longer than 60,000 miles. So notice the alternative hypothesis there matches the sentence better because we want to know, is it going to last longer? That's what we're investigating with that claim. And in particular, that's why when you look at the ha that I've highlighted in red, it's the greater than. But notice your ho still has that equal to in it. The ho will always have some sort of equal to it and part to it, because that's what we use to build the distribution to test this with, just so you know. That's a view to the future. So then you look at the ho, and it's the opposite, and it's the one that has the equal sign in it. So remember, ho is about sameness, boringness, equality, nothing changes. We want to see if it's going to last longer than what they claim. All right, last one. Testing the claim about a population, I think that the medical clinic has a wait time on average that's less than 15 minutes. So that's again an alternative because we're talking about just a less than, and yeah, that one's not that interesting. Usually when I'm doing these, I also will take the time to write out the units. So the first one would be ounces, the second one would be miles, and the last one would be minutes. This is just a good habit to get into to remind yourself that this is quantitative data, and that's why I'm looking at means here. So what are we up to with the hypothesis test? We're testing for consistency. We're trying to see, does my sample show that this is consistent with the null hypothesis or not? So when you gather the sample evidence, you want to ask yourself, is this sample unusual if the null were what was going on? If it is, then it's good evidence that your null seems to be reasonable and seems to be what is going on. If it doesn't, or if it's unusual sample, or if it's really far away, or if it seems to be something that you just shouldn't get on your first sample try, then it seems to be inconsistent with the population mean, in which case we're going to reject the null hypothesis and go with the alternative as what's going on. So what we're going to do is we're going to gather sample evidence and say, does it point towards this hypothesis or the other one? Does it point towards the null hypothesis or the alternative? That's what we're going to get up to. All right, so there are three types of hypothesis tests. Specifically, there are two categories. There's the two-tailed tests, and then there's the one-tailed test. So the two-tailed test, you could go in either direction. I think that when I look at the sample mean, it shows an inconsistency that could be greater than or less than. So this is like with the cereal example where I was like, hey, it could be 16 ounces or not. It could be smaller, or it could be larger. I don't care which direction it's going, or if it's bigger or smaller. I just care, is it different? Yeah? Now, if I cared about whether or not it was larger, that would be an upper one-tailed. So there's two types of one-tailed, the upper and the lower. So the one that I had previously was about the Goodrich tires lasting longer than 60,000 miles. That would be an example of a one-tailed upper test because you want to see, hey, is it going to last longer from our alternative? So you'll notice for the type of test, we really look at the alternative hypothesis. All right, and then for the smaller, that goes with my, hey, is my wait time less than 15 minutes? Because I'm looking to see, is it smaller than what we hypothesized based on what I gain in the sample? Let's do a little bit of practice with this. So for each of these examples, what I'd like you to do at this stage is pause the video, read this, make your own hypotheses right now, write them down, and convince yourself whether or not you, well, sorry, not convince yourself, see whether or not you get what matches with me. Obviously, if you printed out the notes, you already have the answers, so that's no fun. Well, maybe it is fun. I don't know what your definition of fun is. Anyway, here we go. Answer coming in 3, 2, 1. Bing! Okay, so notice we want to see is an exceeding 33 minutes. So exceed means more than or greater than, so that's where the alternative is coming from. So notice the subtlety of the notation with this. In particular, this part here is just telling me or marking this is the alternative hypothesis. This part isn't so important. It's just like, hey, this is what this is. This is a label. L-A-B-E-L, I think. Why did I use a word that I'm not sure I know how to spell? Anyway, then you'll notice right here, there's my mean time spent by people in downtown's parking spaces. Be careful, although we use this symbol for every single population mean, this one is specifically for the mean time spent by people in the parking structures. So be careful when you look at this. That's what it's standing for. When you look at this hypothesis right here, it should match your sentence. Mean time is greater than 33 minutes. See how I'm reading this? Yeah? And then that exceeds portion is what's telling you that this is a greater than. Yeah? And then the ho, which we labeled like this. So again, these are just labels. They're not as important as the next part. This part is the important part. Notice it has the equal to part because it's the ho. It's got to have some sort of equality or sameness in it. I always think of just the ho as like the equal boring version of the alternative, and that seems to help me. I hope it will help you too. Anyway, so this is the claim I'm interested in testing and what was described in the question. Always the alternative will be described in your question, and then you'll produce it and then the hoe, this is one of those weird things about math that I'll never understand because I'm not the person who invented this. Why do we write the hoe first when it's the claim in the sentence that we get first? I don't know. I wish I knew the answer to that. I might have to go some digging in math history and figure that out. Now I'm just rambling. Let's do the next one. Okay, we're looking at some agriculture. We want to see, is the average rainfall in a particular county at least 23 inches? So when looking at this, to me, that looks like an alternative hypothesis. And then my mean is going to be the average rainfall. So I'm using, average annual rainfall. That's where my mean is coming from. And I want to say at least 23 inches. Now, at least is something that bothers a lot of people and that they have a lot of difficulty with. Because when they see the word least, they think it means like less, and then they write less than 23 inches, which is absolutely not what is going on here. At least actually means greater than or greater than 23. So when you look at this, you're like, oh, at least, what does this mean? Greater than or equal to 23. Why? So I always think of this in terms of carnival rides. If you have to be at least 5 feet tall to ride the ride, if you are 5 feet tall, you can get on. If you are not 5 feet tall, you can't get on. Yeah, if you're under it. So this is going to be something with greater than or equal to. So I'm going to write my 23 in here, my 23 in here. So clearly that's what my claim is about. I'm going to write my hoe. Whee! Okay, and then the big thing about at least is if you write it symbolically, it's going to be a greater than or equal to. Since it's the one with the equal to, I'm going to be placing it for the hoe. And then my ha will be my less than. So when you look at this, there's your hypotheses. I'm going to cut that part out if I can. I probably can. Anyway. The company that fills a popular soft drink sets a filling machine so that the mean contents per bottle is equal to 12 ounces. I say this is a two-tailed test. The reason I know is because there's nothing in here about being lesser, greater, or smaller. So this to me feels like it's just going to be a difference test. And there you go. The status quo is that it's actually equal to 12%, or sorry, 12 ounces. And then the obvious version opposite to that is not equal to. So another thing to keep in mind about not equal to is this is the default. If they do not give you anything in the question that tells you if you're looking for, is it greater than or less than or exceeds or at least or at most or any of those keywords that tell you something about symbology, you should be using not equal to. So if they just say a statement like this one where, oh, they say the contents is this, you're testing a claim of is it this or not, and that's where you get the not equal to from. All right, a customer buys a pipe fitting, I said that wrong, I'm so sorry, from a supplier, claims that the mean diameter will be 2 inches, is not equal to 2 inches. I forgot to make this one do a animation, but clearly when they just flat tell you not equal to, that's going to be your alternative hypothesis. And there you go. And remember, the hoe is boring and is always just an equal to version of whatever your ha happens to be, if that's what's described. Ah, finally another one I animated. Yay! A pharmaceutical company produces a new drug to treat heartburn. Yeah, that's part of getting old. The company believes the drug will stop heartburn in less than 15 minutes. So this is a straight less than. You should be looking at that and thinking, oh, that's going to be this guy. That has no equal to in it, so that's definitely going to be my alternative hypothesis. And then my null hypothesis will be a greater than or equal to. So there's what she looks like. I hope this time with hypotheses helps you, because without correct hypotheses, your tests really do not run well with hypothesis testing. So let's take a look at the logic and an example of a two-tailed test so you can see what these actually look like as you perform them. All right, so we've got an alternative and null hypothesis up here in the corner. So pay attention to these two. So I'm testing to see, is my mean 100 or not? And so what I want to do is I want to gather a sample mean and see if it's consistent with this idea. So I take the null hypothesis and use that to place my center. That's why it's important that your null hypotheses have equals in them, because if I'm trying to place my mean as something greater than 14, well, which value is it? Because there's an infinite number of values that are greater than 14. If I have greater than or equal to 14, then I can use the equal to, because I know where it starts at 14. It could be larger, but we know where to start, and that builds our initial value for our hoe, and that makes the center of our distribution. So you'll notice in here that I've marked off two values in the tail at 80 and at 120, and this is when we're going to decide whether or not something is inconsistently larger based on the sample mean or consistently smaller based on the sample mean. So what am I doing here? So I've got my center, and then basically I'm going out in each direction about 2 standard deviations so that I have about 95% in the middle. Most of the time we'll do this a little bit more accurately than what I'm doing in this picture. I'm just doing an estimate. So 95% of all stuff is in the middle. And so out here I've got the very small improbable tails of 2.5%, or things that are just really unlikely because they are so small in probability. So here's the idea. If I go out and I gather a sample mean, if this is my population mean and I get something like 130, that's way the heck out here. That's very unusual compared to what I claimed it's going to be. That seems like good evidence that the null is not true. Now, however, if I went out and gathered a sample and it was something like, I don't know, 98, so it's like right here-ish. Oh, well, that's really close to my population mean. That seems to be good support that this is actually the population mean, because when I gathered my sample, it was very close. It seems reasonable that the null is the truth. See what's going on? So we call these regions rejection regions because they're places where if you land there with your sample, so your little X bar lands like here, or maybe it lands like here when you go out and gather your sample evidence, it's going to be a place where you'll reject the null hypothesis. You'll say it's inconsistent or too large compared to the sample mean. And if it's over here, it'll be inconsistently small. It's too small of a sample mean compared to my population mean. Let's take a look at how this looks for an upper tail. So same idea. So notice my rejection region is only on one side. And over here, I've got this little area where I'm like, hey, it looks like it seems like it's inconsistently large compared to my my null hypothesis. And notice that this was about the mean being smaller, so that's why we're using this upper one, because we want to see, is it going to be unusually large? Another way to ask yourself about this is it good evidence for the alternative hypothesis? And the alternative is about, hey, I think it's greater than 100, so I want to look at things that are bigger. Is it big and unusual? So if it's over here, then we're going to say, hey, it looks like it's too large. That appears to be something that's not good evidence that our mean is under 100. All right, lower tail now. So same idea. If it's too small, it ends up over here in the lower tail. So when I say it, I mean the sample mean. So we start out with the null and alternative hypothesis. We go out and we gather a sample, and we ask ourselves, if we compare it to the null, am I convinced that it's unusual? Am I convinced that it should be the null or the alternative that's the truth? So if I get something that's small and over here, so if my sample mean lands like right here, it's very small compared to what I claimed the hypothesized mean is going to be. That seems good evidence that it's not the null hypothesis, but actually the alternative. If I get something that lands anywhere over here, like say, oh, I ended up a little crooked, so if my sample mean lands like over here at like 111, that's fairly close to my null hypothesis, and it's also greater than my null hypothesis. That seems to be good support for my hoe that the mean is greater than or equal to 100, because it matches it. So if you go out, you gather your sample, and it seems to match what your hoe is saying, we claim that the hoe is the truth. If we go out and gather our sample, and it seems to match the alternative, we're going to say that the alternative seems to be what we support. All right, so here's how I want you to think about this. And this seems a little crazy if you've never been a part of a jury trial. This might seem insane. So the law system we use is based in the United States is based on the British common law system. And really what this is about is the assumption that you're innocent until proven guilty. So we want to think of the null hypothesis as like our defendant. They're innocent. We don't know if they're the truth or not. We don't know if they're guilty or not. We assume they're innocent. We gather some evidence and we see, does it seem to contradict their innocence, in which case we would declare them guilty, or does it seem to support their innocence, in which case we would declare them not guilty. So they start with the presumption of innocence, aka the hoe is the truth, and then we use that to build our distribution, and then we gather our sample evidence, aka the evidence for or against the defendant, and then we declare them either guilty or not guilty. So what's interesting about this is, notice, like, we presume they're innocent, but you never declare them innocent, you declare them guilty or not guilty. So you're going to see me do this with the hypotheses. I'm going to say, oh, my evidence supports this one, or my evidence supports that one. I'm never going to declare one of them the truth. This is a little bit of a weird thing about how we describe hypotheses. All right, significance levels. This is our cutoff for when we have significant evidence against the null hypothesis. The significance level is known as alpha. It is a probability. It's usually, if we're looking at typical values of alpha, we'll use like 1% or 5%. Those are the fairly typical ones. And I've seen somebody use 10%, but really that's kind of big as far as something that seems significantly small, if you know what I mean. The generally accepted value you should use, if you're not sure which one to use, is 5%. In general, most problems when you are not sure what the significance level should be will be given to you. So like I will tell you, use a cutoff of 5%, or use a significance level of 5%, or 0.005, or sorry, 0.05. And when I want smaller, I'll tell you, like, use 1%. So this value in particular, this cutoff right here, is the place where you start to fall into the region of you're too small or too unusual to be considered a reasonable value. All right. So how are we going to use cutoffs to make decisions? So we're going to look at the cutoff, and when we gather our sample evidence, if our sample is larger than the cutoff, we're going to reject our null hypothesis. If the sample is less than or equal to the cutoff, then we're not going to reject our null hypothesis. So this is what I was talking about earlier when I was saying, oh, hey, if my, if I gather my sample and it lands right here, clearly that X bar would be less than the cutoff, so I would not reject my null. It seems to support it. But if I landed over here with my sample, oh no, it's, larger than my cutoff, I would reject. Now, similarly, I have drawn this using the hoe and ha from earlier. So my hoe was that, sorry, my voice has decided it suddenly sucks, is less than or equal to 25, so smaller than, and then my ha was a greater than. I'm sorry, I should have included this on the slide. Greater than 25. So I want you to imagine what this would look like if you were looking at one that was flipped, so where I was looking at a greater than or equal to. So then my rejection region would be over here on this side, and a two-tail would have two of them, either too big or too small. Let's look at some methods. So how we're going to conduct our hypothesized test, we're going to calculate our standardized value, either a critical A, or critical T or critical Z, and then calculate our mean sample value or p-value to decide, is this unusual or not? So I'm going to be showing you two approaches on how to do this. We're going to be using these two for the critical value approach, and for a p-value, that will be using a probability approach. Probability. Woohoo! And then these two combine to make what's called the cutoff approach or critical value approach. Critical. Anyway, so we're going to look at values and use that to determine, is it unusual or not? Let's take a look at the steps behind this. So we have a home building company that wishes to test to determine whether or not a mean time to frame a roof in a new home is 25 days or less, or fewer, sorry, and the standard deviation is known to be 3 days. So the fact that we know the population standard deviation right here, that tells me that I'm going to be using a Z, not a T. Because if you know the population standard deviation, you don't have to use T. So I'm going to use a cutoff of 10%. Again, this is a little unusual, but we're still going to use it every once in a while. And then we have a random sample of 24 homes, and we take a look at their sample mean. So this is my X bar. That's going to be my sample information. We want to draw our conclusion based on this. So looking back that roofing a home takes 25 days or fewer, that's going to be a claim about my population. So that's going to be what I use to build my null hypothesis here. So here we go. So there's my null hypothesis. And then down here, I'm going to be using the sampling distribution to find what's called the test statistic. So the test statistic tells you where the sample value will lie on the standard normal distribution. So what you do is you put your sample x in, so that's 26, and then I steal the value from my null hypothesis, because remember up here I said, oh, the mean is, there's the one with equal to 25, so that goes there. Down here, notice we're using the spread from the sampling distribution, because we used a sampling of 25 homes. So this is the appropriate spread to use for this, not 3. We're using the sampling distribution because I have a sample of 64 homes that I'm using. So I'll calculate that z-value, and it's 2.67. This should strike you as a bit unusual already, since that's pretty far away from the mean of the standard normal distribution. The mean of the standard normal distribution is 0. Just as a reminder, its spread is 1. Remember earlier when we encountered the 68, 95, 99.7 or empirical rule, we said that being 1 standard deviation away is 68%, being 2 away is 95%. So yeah, that's a little unusual. Okay, so using the standard normal table, I'm going to look up Z10, which means I'm going to look up 10%. So this is a probability on the table, and then use that to get the Z-value that goes with it. I place that value on the distribution as my cutoff, and then I'm going to use my Z-value that I've got over here to decide if I'm going to reject or not. So since my, my test statistic is larger than my cutoff value, I already know I'm going to be rejecting. It's far enough away from the mean to where I should reject my null hypothesis. So I would look at this and decide to reject my hoe. Isn't that fun? So my z was too big, so I'm going to reject the hoe. It appears that I have evidence that the alternative is what should be supported. So what I should say next is, oh yeah, it does look like it's going to take longer than 25 days on average to roof homes, because that supports my alternative hypothesis. So I'm going to use this to make my decision. So I decide, looks like it's longer than 25 days. I should watch my project planning. Because of that, it's longer than what I expected. Let's look at another one. The next one's going to be two-tailed, so prepare thyselves. Okay, so let's take a look at a two-tailed example. We have a oatmeal company who they want to see, does their filling machine actually fill what's supposed to be on the box? So if you notice, any type of food you buy always lists what their filling is supposed to be, but if you weigh them, just one of them, rather than weighing them on average, you won't always get the exact same amount as what it says on the box. So they say their mean filling volume is supposed to be 16 ounces, and they want to determine if the machine is still filling with that. So they want to see if they want to adjust it, essentially. So the machine has a known standard deviation equal to 0.422 ounces, and it's normally distributed. So that's super telling me this is going to be a Z, not a T. And from these two sentences about whether or not it's filling correctly, that gives me my hoe is that I think on average it's 16 ounces. And then my ha is I think it's not filling correctly on average, so then it's not 16 ounces. Got it? All right. And then we know the sampling spread, that's good, and we know how big our sample is. And there's our sample mean. So they gathered a sample of 49 cereals, and that was the mean it had. Perfect. Let's conduct ourselves a hypothesis test. So I've got my hoe and my ha. I can use that then to do my test statistics. So remember, this is always coming from the hoe, the statement of equality. We're always using the spread for the sampling distribution for a mean. So that's always the mean of the sample or the known population spread divided by the square root of the sample size. That's 3.32. I already know from looking at this that that's very unusual. That's a very large z-score value. This is probably going to be a reject. All right, now let's build our distribution. So remember, you use your hoe to build your center. That's a horrible arrow. So there's my mean, which is equivalent to z being 0 if I look at the standard normal distribution because its mean is 0. And here's where things get a little weird on the two-tailed test. I'm going to take my significance level of 10%, which I gave to you right here, and it actually gets divided between the two tails. Since I don't have just one tail, we're going to divide it into 2 equal pieces to put 5% in each tail. Woohoo! And if you look that up on our z table, so I'm looking up 0.05, I get 1.645. I'm also going to show you how to do that on Minitab this week in case you're really uncomfortable with the table. For now, just accept that the cutoff is 1.645. You may also notice that these are common values for critical values or Z stars that we used for doing confidence intervals. They are absolutely the same idea. Anyway, so I look at the Z value right here of 1.645 and compare it to the Z value I got from my test statistic, and I notice my Z value for my test statistic is larger than the cutoff. That tells me I will reject the null hypothesis. So I was just walking you through this part right here. Since I reject the null, it does look like that my machine is not filling at the 16 ounces it claims to be. It actually looks like it might be larger than that. Uh-oh, SpaghettiOs, or I guess uh-oh, oatmeal. We should probably recalibrate our machine. It's not filling correctly. All right, let's take a look at a one-tailed test. We're using critical values. And did I already do one like this? I already did a greater than, didn't I? Yeah. Let's do another one. Okay, a home building company wishes and determines whether or not the meat. This is exactly the one I did earlier. Why do I have it on here twice? Oh, what conclusion should be reached? I already told you what this was. Crap. This slide doesn't need to be here. Yep. So remind yourself of the home one. I don't remember why I have this here. Why am I still talking about it? Yep. I don't. Yep. I'm probably just going to delete this. I don't know why this is here. Yeah. Let's talk about the p-value approach. I prefer the p-value approach because it makes a lot more sense to me. Basically, our idea of doing this is we are going to gather our sample and then find the probability we get that sample or something significantly more worse based on our alternative hypothesis. If that p-value is small, it's evidence against our null hypothesis. If our p-value is large, it is evidence for our null hypothesis. Our cutoff for whether or not our p-value will be large or small is by comparing it to alpha. So instead of comparing it to x values, we're going to compare probabilities. So the idea being that instead of looking at cutoffs and values themselves, I'm just going to be looking at probabilities instead. Got it? So I'm going to repeat some of the examples I just did, but using p-values. All right, so let's take a look at the p-value approach. So this is the same setup as the oatmeal one, so hopefully everything on here is fairly familiar since we just did that one a couple minutes ago. What you want to do here is you want to take a look at your random sample, and we want to find the probability that when I look at my sample means, I get 16.2 ounces or something bigger. Now I'm picking bigger because I know that 16.2 is greater than 16 ounces, and I want to go more extreme than the value that I have. So in which case I'm going to do larger. Now because this is a two-tailed test, I need to make sure that I account for the other tail as well. So I'm going to double this because the other one has been, the probability and the significance level has been doubled as well. So what you would do at this stage is you would go to Minitab, you would type in 16 ounces as your mean. Your spread or standard deviation in Minitab would be the 0.422 divided by the square root of the 49 boxes that you got. You would enter in 16.2 and do a right tail, and that would give you a probability. And don't forget that 2 out front of 0.0005, which gives you a p-value of 0.001. Super small. How small is it? Is it less than the alpha of 10%? Yes, it is. So since my p-value is smaller than my level of significance, it's significance evidence against my null hypothesis. So that tells me that, ooh, super small p, I don't want no hoe with a small p. So this is the stupid way I remember this. It's a small p. I don't want no small p. That means I want to reject. It's dirty and it's stupid, but it's easier to remember than the other one. This is why I like p-value approach. I feel awkward. Okay, so I'm going to reject my null hypothesis. It appears to be evidence to support my alternative. It looks like it's not filling at actually 16 ounces. We should probably work on our machine, man. Okay. Let's take a look at the same test using, oh no, this isn't the same one. 16 ounces fooled me again. I forgot. This is the milkshake test. All right. In this one in particular, I do not know my standard deviation on my population. Oops. So in particular, I'm not going to be able to use Z. I'm going to have to use T. So we look at the volume of a milkshake filler, and it's supposed to be 16 ounces. So to see if it actually matches what the filling weight should be, we do a random sample of 16 shakes. Notice the small size. That also means I would have to use T. And I notice that the sample mean is 16.93. Now this is less than the 16 ounces, but what you want to know is it so small that I'm convinced that yes, it's not filling correctly? Keep in mind, you don't want to look at that and be like, oh, well, 15.93 is less than 16. Done. That's how a naive person who does not understand statistics and not understand distances would approach this. Because what you need to be able to tell is this far away is you need a spread. Because without spread, you can't tell is it far. Speaking of spread, the sample standard deviation is 0.5 ounces. I'm going to use a alpha or significance level of 10%. I kept telling you guys it was unusual. Don't ask me why, but your textbook fucking loves 10%. So it's in here a lot. We're going to use the t-test approach to do this, and we're going to fill the distribution as normally distributed. Anyway, so here's your hypotheses, and here's my alpha. So we create our rejection region as half of that. So I'm coming up with these t-values from the following. So this one is the one from the test statistic. Usually I'll label this as t-stat just so I don't get them confused. If you want to do that, you can do that as well. And this is just doing what we normally would do. There's my sample value. There's my one from my hoe. Boop, 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 boop. And then there's my standard deviation from a sample. Notice it's S. And then my 16 is from, I have 16 in my sample, so there is my T value. Remember, T is different from Z, so you can't really tell if this is unusual or not. I need to calculate my T value. So to do T values, this is where you're going to need to pull out your T table and or use Minitab to calculate the T cutoff. So you put in 0.05% and you use degrees of freedom of 15 and you get the following value for T. So that tells me this cutoff right here. And that will give you, sorry, that your T-stat, your one from the test statistic, is larger than your T cutoff. So in particular, this is not an unusual t-value, and therefore it's not evidence against my null hypothesis. I can't reject it. So I can't really conclude that the mean filling is 16. I have evidence that supports it. So it looks like the mean filling ounces for this milkshake could be 16 ounces. So notice how non-committal about this we are. Could be. Yeah? Because remember, you can only say where the evidence points you, not a definitive truth. Yeah. Not going to declare innocence or guilt. Just going to say what my evidence supports. All right. Let's take a look at doing this for a proportion. So I'm going to take you through the exact same stuff, but for a proportion. So in particular, a couple things will change. My mean, just like we saw with the sampling distribution, is going to be a proportion. My sample stuff is now a p-hat because it's a sample proportion, but everything else remains the same. You're still doing a hypothesis test, you're still looking at significance levels, you're still doing cutoffs, you still have all the tail options. Everything stays the same. All right, so one-tailed tests are not equal, are the ones that are greater thans or less thans. The two-tailed tests are the not equal tos. Notice the change in notation. So in particular, we have P's because these are proportions, not means. I know some of you may have encountered some difficulty with this idea when we were dealing with sampling distributions. Proportions go with categorical or qualitative data, not quantitative data. Quantitative data are the numerical data that have units. That's the kind of stuff we can add and divide by how many we have because they're values or numbers. Those are the kind of things that you can do means of. Proportions are things you can't do means of because there are things like yes or no questions. I can count how many yeses I have though, and that will give me a proportion. Just like we've seen before, and I've already mentioned, it's categorical values, it's successes and failures. For examples like customers that like a product or not like a product, how many defectives I have, how many non-defectives do I have, stuff you can count. Countable things. Yeah. So what do? We're going to specify our parameter of interest, form our hypotheses, specify our significance level, use this to conduct and create a rejection reason. So what I mean by that is either we're going to do the critical value or we're going to perform ourselves a p-value test. So we're going to do one of the two. All right. Once we have that, things get a little wonky because 5 and 6, depending on which version you're doing, or sorry, 6 and 4, or depending on which version you're doing, are a little bit different. We're going to calculate our test statistic. Notice that our test statistic is based on the sampling distribution of a proportion and is always a z. So with means, we have the problem of is it z or is it t? What type of data do I have? With p, it's always a z. So that's one thing that's kind of nice. And then we will decide on which one seems to be supported, my null or my alternative, and draw our conclusion. It seems like there's a lot of steps here. Back in the day when I did this, there was only 5 steps. The reason why there are so many steps here is because I'm including both ways you could make your decision, both the critical value approach and the p-value approach. All right. A company claims that the proportion of dissatisfied customers is less than 10%. To test this, a simple random sample of 100 customers is selected and 6 are dissatisfied. Cool. Using a 5% level of significance, conduct a hypothesis test using the Z statistic approach. Okay, so less than 10%, that feels like an alternative hypothesis to me. There she goes, right there. Ta-da! So that tells me I'm going to be a one-tailed test. I have my alpha level as 5%. I picked that. Yeah, okay. No, wait. Yeah, I put it in this problem. Sorry. And then I know that my n is 100 and that my number that we're dissatisfied is 6. That's my capital X or little x. It's the number of people that have the attribute I'm interested in. So that's why this is 6 out of 100 down here, or 0.06. So I'm going to form my rejection region of 5% based on alpha. I've placed my value of 0.1 here based on that's supposed to be a fancy lowercase p. It looked like a mean for a second there. That was bad. There's my mean of 10%, center of the distribution. And then we need to find the z value that goes here so we can determine, based on the z value approach, will this value be unusual or not? So when I say this value, I mean the p-hat, or sorry, p-bar. Oh, yes, and to be able to figure out if it's unusual or not, I will need to figure out its z-score, and so we need its spread. So da-da-da-da. Notice that when we're calculating the spread here, we are using the HO, not 0.06, the one from the null hypothesis. This is incredibly important, so I don't know, put like little hearts and stars in your notes about how important that is. That was my weird yield sign symbol that helps, I think. I don't know. Anyway, to finish this up, we need to do some calculating. So down here below, this is where we should start. I need to calculate my z test statistic. Stat. So I'm going to do my sample minus my proportion. Boom, boom. Divided by my spread, and we get the following value for z. That's not that unusual, so I'm not too much of a shocker there. If I do a left tail probability on the standard normal distribution with 0.05%, that'll give me the following z value. You can also find this on your table if you want to, of 1.645, and then you notice negative 1.3 is greater than that, so that seems to say I'm not going to be rejecting my null hypothesis because it's not in the rejection region. So thus I can conclude the proportion of dissatisfied customers is less than 10%, since this seems to not support the null hypothesis that they claimed. Yeah. So notice the whole not here. If you wanted to phrase this a little bit differently, you could. Kind of depends on how you like to write stuff. Okay, let's look at a different approach. So here I'm going to use the critical value approach, where I'm going to find the p-bar that's associated with the appropriate critical value and use it to decide whether or not I'm going to reject or not reject. So a manufacturing company believes that the proportion of defective products is no greater than 0.01. To test this, the quality department randomly samples 600 products. Ooh, 600 is kind of a big sample size. Anyway, and found that 9 were defective. Okay. That's not that many. We're going to use a critical value approach with the alpha being 0.02. That's a little unusual. Anyway, so the whole no greater than 1% tells us what our null hypothesis is going to be and our alternative hypothesis is going to be, which you'll find down here. And then there's my alpha. It's just nice to summarize those before you get started. You'll notice over here I've calculated the spread, which I'm going to need to determine my z-scores, and in particular to be able to find my critical value cutoff. So just a reminder, this is essentially like doing a confidence interval. I'm going to take my sample value of the proportion and add my critical value of z-score times my spread, which we found here to be 0.04. That's this calculation here. You find that to be 0.182. So, I hate this approach, I'll be honest. And then you look at your sample and you're like, oh my gosh, it's 0.15, which is, you know, smaller than my value. So it's somewhere over here, right? There's where my p-bar actually is. So my p-bar did not fall in the region of rejection. It appears that I'm going to not reject my null hypothesis. Oh no. So I would appear, it would appear, oh my gosh, I would appear, what am I talking about? It would appear that my evidence supports my null hypothesis. It looks like the proportion of defective products is no greater than 1% like they claimed. So they were right with their belief there. Kind of nice. All right, I know I've reached the end and things may be a little scary. Minitab will help you severely do all of these calculations if you're very worried about it. As long as you've been comfortable with our last week of doing a bunch of probabilities, this week should be easier because of that. As always, there's a copyright warning of how you're not supposed to post this anywhere without my or Pearson's permission, because some of the examples I used today and images I used today belong to Pearson. That's all I got. Make sure you watch some of the extra examples. They are very important this week.